The throttle actuator control replaces the need for mechanical linkage between the throttle body and the accelerator pedal. It also replaces the need for an external cruise control module and an idle air control valve. TAC systems enable the integration of adaptive cruise control, electronic stability control, traction control, and active braking control with the engine management system. Removing the amount of moving parts also saves money and reduces servicing costs. A TAC system consists of an accelerator pedal, position sensors, an engine control module, and a throttle body assembly. The driver's torque request is communicated to the ECM via an accelerator pedal voltage signal. With this information processed, the ECM can command the throttle valve motor open or close, achieving the desired torque. The ECM can make adjustments to the throttle valve without the input from the accelerator pedal. Fast idle can be seen during cold start conditions or when the air conditioner has been turned on. The ECM may command the valve closed during a traction or active braking control moment, regardless of the driver's torque request. A TAC system on a common rail diesel has no control over the throttle valve assembly. The valve is normally in a wide open position. Again, the job of the accelerator pedal position sensor, or APP, is to convey the driver's torque request to the ECM. There are different types of APP in use in current motor vehicles: a variable resistor with 2 position sensors for redundancy, or a contactless position sensor. Let's take a quick look at a potentiometer type APP sensor. A 5 volt and low reference is sent from the ECM to APP-A, while a signal return goes from the sensor back to the ECM. This is monitored either by a pull-up or pull-down resistor. Again, a 5 volt and low reference is sent from the ECM to APP-B, while a signal return goes from the sensor back to the ECM. Again, this is also monitored by either a pull-up or pull-down resistor. The output voltages at APP-A and APP-B will be different. Both voltages communicate the degree of pedal angle to the ECM, and if a fault occurs, they may be used for diagnosis. On this vehicle, at rest with no driver input, the sensor voltage for APP-A is 0.96 volts, with APP-B starting at 0.47 volts. When fully depressed, APP-A will be 4.72 volts, and APP-B will increase to 2.35 volts. By using the oscilloscope to monitor these values, we can see the voltage change easier. As the pedal is slowly depressed and released, we still have the same voltage values as the scan tool, but any discrepancies between APP-A and APP-B will become obvious. This is seen as an analog signal. The second type of sensor is a contactless sensor. Hall effect sensors change their output voltage in response to a magnetic field. They can be used for proximity switching, speed detection, and in our case, accelerator pedal angle positioning. The Hall sensor and permanent magnet are mounted within the pedal housing separated by a fixed air gap. Reference voltage and ground are supplied from the ECM to the sensor, while the signal position is returned to the ECM. As the pedal moves through its range, the current flow through the Hall layer is altered. This alteration of current flow is then conditioned and amplified. The output signal is now interpreted by the ECM as a pedal position value. The advantages of using this type of sensor are the output signal is more accurate, they are shock, temperature, moisture, and dirt resistant, and have a longer service life than the potentiometer type predecessors. Another way of measuring rotational position is by using inductive coils. An AC voltage is induced into the output windings through excitation of the input windings. The output voltage will vary based on the angle of the accelerator pedal. At rest, with no driver input, AC current flows through both windings. Their values will be equal. As the pedal angle changes, so does the amplitude of the output winding's phase angle. This signal is then conditioned and amplified via an integrated circuit for either digital or analog output. These coils and electronics are mounted to a printed circuit board. The accelerator pedal is equipped with a heavy return spring for a simulated feel and has about 60 degrees of travel. Within a tax system, the ECM's role is to process data received from the APP sensors and then command a throttle valve movement according to these inputs. The ECM interprets the data and then, using a multi-dimensional map, plots the optimal throttle valve angle based on the sensor's information. From there, it can further adjust fuel delivery, cam position, and ignition timing to enhance driver request torque output. Serial communication may then be used to relay this engine data to other control modules within the network. If the traction control module detects wheel spin, the ECM will relax the throttle valve angle, reduce the amount of fuel being injected, and retard the ignition timing. The active cruise control module communicates with the ECM, adjusting the throttle valve angle to adapt to road and traffic conditions. Although this is possible using a mechanical linkage and vacuum assembly, utilising an electronic tax system instead enhances reliability and has a much finer control over engine speed and torque delivery. This type of throttle body uses a bidirectional motor, a heavy return spring, and 2 variable resistor sensors. There are different types of throttle valve position sensing methods. Just like the APP, there is contact and contactless. Again, the contact type is a potentiometer, using carbon strips with its position voltage. The ECM supplies the TPS with a high reference and a low reference circuit. The sensor returns a signal via a pull-up or pull-down monitored circuit. The hall sensor and permanent magnet are mounted within the throttle body housing, separated by a fixed air gap. Reference voltage and ground are supplied by the ECM, with the signal position returned. As the throttle valve moves through its range, the current flow through the hall layer is altered. This alteration of current flow is then conditioned and amplified. The output signal is then interpreted by the ECM as a throttle valve position. Sounds familiar, right? That's because they share the same common architecture. Sharing technology saves the manufacturers money and may also be integrated into other vehicle systems. Another type of TPS is the contactless inductive system. Again, the same principles from the APP apply. Using inductive coils, an AC voltage is induced into the output windings through excitation of the input windings. The output voltage will vary based on the angle of the throttle valve. On this vehicle, our signal values at rest are TPS-A 0.86 volts and TPS-B 1.69 volts. When the throttle valve opens, TPS-A increases to 3.92 volts, while TPS-B changes to 4.14 volts. Again, using an oscilloscope will immediately show any discrepancies within the system. On some newer vehicles, when the ignition is first switched on, you may hear the throttle valve moving. Some manufacturers use this as a self-test procedure. The ECM monitors the TPS voltages for any abnormalities. If any fault is found, the mill may illuminate and the ECM may command a reduced performance mode. If there is a complete failure of the throttle valve assembly, the vehicle may still be driven. With the throttle valve unplugged, we can see that the throttle blade rests at around 25%. This is a design feature in case there is a fault within the valve assembly. Engine torque is regulated using controlled misfire events. When the engine is shut down, the throttle valve is pulled closed for a predetermined time. This prevents engine run-on by restricting all air from entering the combustion chamber. On some vehicles, a real-in of the throttle valve assembly may be required if the battery voltage has dropped below the minimum threshold, or the valve has been replaced. A relane procedure is simply teaching the ECM where the throttle blade sits at idle and wide open throttle. Pretty clever stuff. And it's only going to get harder and more complex. Knowing how a TAC system operates will prevent misdiagnosis. Thanks for watching. See you soon.